Can you guys hear me and see the screen?
Yes. Yep.
Yeah, I can.
Okay, thank you. All right, good morning. So today we're going to have a very fun lecture. It's also going to be a little bit tough because we'll discuss the basics of quantum mechanics. As I've told you before, I don't want you to freak out if you don't understand every nitty-gritty detail, because all that I need for this course is to have a general physical understanding of the principles of quantum mechanics. I'm not going to give you complicated quantum mechanical problems in exams and things like that. Okay? All right, so let's start off with a quick review of what we discussed last week, where we introduced the basic concepts of quantum physics, which predated quantum mechanics. So quantum physics led to the mathematical formulation known as quantum mechanics in the 1920s by many people, but Heisenberg, Schrodinger were two of the key folks. Okay, so the basic physical concept can be understood beautifully by looking at the so-called double slit experiment that we discussed last time, where we said that if you have a light source, a point light source at S, which shines through a screen which has two holes cut in it, and then the light intensity pattern is looked at a screen on the right-hand side, Then if you look at the screen head on, what you see are these bright bands of light, dark bands, bright bands, light bands. And that was explained by folks like Huygens as being evidence of light propagating as waves, because if you have waves propagating from this point source through these two slits, through the different points on the screen, at certain locations, because of the distance from the two slits, in terms of the wavelength, at some locations, the waves from the two slits end up matching in phase, giving you constructive interference. But in certain other regions, they're 180 degrees out of phase. That gives you destructive interference where you have the dark bands of light, the dark regions, okay? But then subsequent experiments were done where people gradually reduce the intensity or the brightness of this light source. And initially what was found out was these bright bands of light got weaker and weaker and weaker. But then at some point, something funny was observed, and that is, instead of the bands of light continuously getting weaker, people started seeing specks of light, okay, hitting the screen at different locations, seemingly in a random fashion. But then if you do a lot of these exposures, these specks of light over time build up these intensity interference patterns with dark bands and bright bands of light, okay? So it's as if the light is propagated as these particles of light, which we call photons, as first identified by Max Planck and then Einstein. But then the propagation of these light particles, which is the picture that Newton had, seemed to be guided by these waves, these electromagnetic waves. Okay, so that's this wave particle duality of nature. Okay, but then if you think deeply about it, it creates some philosophical confusion, if you will, right? Because just imagine doing an experiment where I shoot one photon today, right? Then I wait a day, and then I shoot my second photon on Wednesday, and so on and so forth, okay? So I'll see these individual specks of light. I'll see one speck of light today, another speck of light Wednesday. I do the next experiment on the weekend, and then I wait a year, and then surprisingly, I'd find that these specks of light, these photons, somehow, although they seem to be randomly propagating through the two slits, over time build up an interference pattern, right? And that clearly is a problem philosophically, right? Because I mean, how the photon that I'm shooting today have any impact on a photon that I'm shooting tomorrow or the day after or whatever, right? So the philosophical picture that has evolved is, you say that although these photons are like particles, somehow they have a wave characteristic also with them. That's a famous wave particle duality, okay? And it's as if the propagation of these particles are guided by the interference phenomena of the wave, which guides the propagation of these particles, okay? Where ultimately where the photons would end up in, the intensity is proportional to the amplitude square, okay? So the power or the intensity at different locations tells you how many photons would ultimately end up in those locations, okay? So the intensity is given by the square of the amplitude, okay? Now that, like I said, creates a problem because, you know, if a photon is an indivisible particle and at the same time it's interfering somehow with itself, it's kind of like saying that, you know, the photon can be either at this slit and the lower slit at the same time for interference to occur, right? It seems to be implying that somehow we are splitting the photon, okay? And these are philosophical debates that people have had for the last 100 years. There's frankly no real resolution. And in fact, Feynman, I'm sure you've heard of him. I mean, he used to joke that, you know, quantum mechanics is, you know, at a deep philosophical level, and no one really understands quantum mechanics, but the mathematics works very well. And all the predictions are borne out beautifully by experiments. So that's sort of the philosophy that we'll also take, okay? So now once people realize that light waves have both a wave character and a particle character, then subsequent experiments done on atomic physics led people to say that, okay, you know, maybe electrons, which initially were thought of as being these charged, negatively charged particles, also perhaps have a wave character with them. And that's, of course, these famous de Broglie waves, okay? So now if I shoot individual electrons through a screen like this, the electrons would hit different spots, seemingly randomly, but then over time, these random spots of electrons would build up a pattern, which can only be understood if you think that the electrons, when they're going, are somehow guided by this de Broglie wave, which undergoes interference, okay? But that, once again, creates a philosophical problem because, you can't split electron, right? So how do you say that the electron wave, which has a certain likelihood of being at this slit or that slit, can interfere, right? Because it seems to be implying that the electron is somehow appearing in two spots at the same time. Once again, these are philosophical debates that have no end at all. So we'll take the point of view of current physicists, that is, let's not worry about the deep philosophical meaning. Let's just look at the math, see if it works, and explain the experiments, okay? So based on that wave-particle duality, we went through a bunch of experiments, the photoelectric effect, black body radiation, and then spectra of lines when you excite atoms. And in the case of atoms, that then led Niels Bohr to explain the model of the spectrum emitted by individual hydrogen atoms, say, as this. So he said that all the heavy mass of the protons and the neutrons are concentrated in the nucleus. That picture was given by Rutherford. And then the electrons with negative charge orbit in various shells or various orbits. Initially, he thought these were circular orbits, but we'll see in general they can be elliptical orbits in various shells and so-called subshells that hopefully you saw in your high school chemistry or AP physics and things like that. But then to explain the sharp spectral lines where you have individual frequencies that are emitted by atoms, which are given by this weird relationship, a constant, which is known as the Rydberg constant, times 1 over n1 square minus n2 square, where n1 can be integers, 1, 2, 3. And then for every choice of n1, you have n2, which would be n1 plus 1, so on and so forth. So to explain that data, Bohr had to make this weird postulate that the angular momentum, which is defined as the linear momentum, mass times velocity, times the radius, which is the distance of the electron from the center, is given by these integer numbers n times h over 2 pi. Now, which of course is a very weird assumption, right? And the only reason he had to make that is to explain the experimental data, okay? Now, h over 2 pi in shorthand is written as h bar. So the angular momentum can't have any arbitrary value, unlike in classical physics. It can only have discrete quantum values given by n times h bar, right? So that was Bohr's postulate, but like I said, he had no real explanation for why it had to be that, okay? That explanation came from this French lord, Prince Louis de Broglie, in his 6-page PhD thesis that he wrote at age 24. He said, to explain the Bohr assumption, we can make a postulate that electrons, which we so far have been thinking of as particles, electrons or any matter objects, okay? It could be electrons or protons or Banerjees, okay? They have all a wavelength, which is given by the same Planck constant divided by the linear momentum, mass times velocity, okay? Now, just as in the case of the energy relation to frequency, the Planck relationship, which is energy equals h nu, you could divide and multiply by 2 pi, h over 2 pi gives you the h bar, and 2 pi times frequency in hertz gives you 2 pi nu or omega, which is frequency in radians per second, okay? So these are equivalent ways of expressing the same expression. Similarly, for the Planck relationship, momentum equals h over lambda. Now, once again, it can divide and multiply by 2 pi. H over 2 pi is once again h bar. Now, 2 pi over lambda is sometimes called the wave number or the wave vector given by the parameter k. So you can write the momentum as h over lambda or equivalently h bar k, okay? Now, as I've told you, these two relationships, the Planck relationship and the de Broglie relationship, are going to be true for everything: photons, electrons, neutrons, whatever, okay? But the relationships between quantities in equation 1 and 2 depend on what kind of particle we are looking at, okay? Now, also, last time I pointed out that these relationships 1 and 2, if you think about it, capture beautifully this wave-particle duality concept, right? Because when you have concepts like frequency, nu, or omega, then you think of a wave, right? So that's the wave part. energy, on the other hand, it's more like energy of a particle and things like that. Similarly, wavelength or reciprocal, which is the wave number, clearly has a picture of a wave, while momentum, we think in terms of a momentum of a particle, right? So that's the wave-particle duality. Now today, we derive relationships between energy and momentum for electrons, okay? And you'll see that relationship would be different for photons, for example, right? Okay? So that's what we'll explain. Okay. Now, so let's see why the de Broglie assumption kind of gives you a physical picture for the Bohr assumption, right? So he said that, okay, if you have this as the wavelength, you can then say that 2 pi r, which is the circumference of one of these Bohr orbits, must be an integer number times h over mv, which is the de Broglie wavelength, right? So that will be a condition where an integer number of these de Broglie waves fit nicely within the circumference, creating the standing wave patterns. On the other hand, if I had this sort of a scenario, right, down at the bottom where n equals a non-integer, say 4 1/3 as an example, then you can form these nice standing wave patterns, right? So that's not an allowed Bohr orbit. On the other hand, if I have integer numbers, say 4 or 5, those would be allowed Bohr orbits. And notice this goes back to the Bohr assumption, right? Because you can take mv to the left-hand side, so that gives you mvr, that's your angular momentum, and then you divide by 2 pi, so you end up getting n times h over 2 pi, or h bar, right? And that's the assumption that Bohr had to make, okay? mvr equals n times h over 2 pi, right? So that made physicists pretty happy because, you know, at least we have some physical picture as to why you have to make that weird Bohr assumption to explain the spectroscopic data. Okay, so what people said was you can't have just any arbitrary momentum and therefore energy. You are only allowed the standing wave patterns in a circular string, just like you have standing wave patterns, say, in a linear string, right? So if you have a string which is locked at these two ends, the simplest mode of vibration would be half of a wavelength. The next mode would be this one, okay, where you have these so-called nodes, which are these crossings at 0, and the antinodes are, of course, the high amplitude points and so on and so forth, okay? Now, once de Broglie had come up with the picture, quantum mechanics was developed by, like I said, Heisenberg and Schrodinger pretty much at the same time, okay? Now, this wave picture creates a bit of a problem, okay? And to explain that, we invoke the language of Fourier transforms, okay? So what did we say last time? Well, we said that if I have, say, a time-dependent signal, f of t, okay? And assume it's a pure sine wave or cosine wave as a function of time, okay? If I have a periodic signal like that in time, and I take the Fourier transform, we know that Fourier transform, say, f of omega as a function of frequency omega, would have a certain distinct frequency, let me call that omega naught, which is the frequency of the sine wave, okay? Similarly, instead of something which is periodic in time, when I have electrons propagating in a crystal, we have functions which are periodic in space, okay? And similarly, now if it's, instead of a time-dependent signal, suppose this is a space-dependent signal, okay? I have some f of x. This would be a electron wave propagating in this periodic crystal, or it could be elastic waves, any kind of a wave propagating in a periodic system, which is as a function of space, could also have a Fourier transform, okay? Now, instead of f of omega, we'll call that f of k, okay? So that's the wave vector that we talked about in the previous slide, okay? So just as time and frequency, omega, are conjugate quantities, Fourier transform conjugates, okay? Similarly, x, position, and k are also conjugate quantities, okay? So you can go from one to the other by taking Fourier transforms, okay? So now, if this is a periodic spatially dependent wave, say in the crystal, I have a certain distinct momentum or wave vector k naught, okay? But then if I ask you, okay, where is this electron, say, located? Now remember, we said that if I have an amplitude A, the intensity is given by amplitude squared, right? And that's how we explain this, this diffraction phenomena through two slits, okay? But now, if I ask you, okay, so tell me where the electron is located, you have to take the square of this amplitude, and you see that you can't really localize the electron at all, right? Because the electron could be over here. If I squared this, could be over here, here, at other locations also with different amplitudes and things like that, right? And that is a problem if I deal with a single Fourier component in the momentum space or wave vector space K naught. All right. So instead, what you have to do is, if I want to say that, I want to take electron and I kind of want to localize it in a certain region of space with a certain degree of uncertainty, say delta X, what I really have to do is I don't work with a single frequency component in K. I have to work with multiple frequency components, okay? And I create a wave packet. And depending on how many Fourier components I have as a function of K with different amplitudes, I can then have an envelope in X, which has a certain uncertainty delta X, all right? Now, you may remember from your math classes that if I have a certain uncertainty now in K space, that then relates to the uncertainty in X space. Just like if I have a certain uncertainty in omega or frequency, that then causes a certain uncertainty in the time domain. Okay, so those are the relationships between the conjugate quantities, okay, when you take Fourier transforms. Okay, so that then led to the famous Heisenberg uncertainty relationship, which says that the uncertainty in X is related to the uncertainty in K, which can then be related to uncertainty in momentum, because K and momentum are linearly proportional according to the de Broglie relationship. Okay, so if I have a delta P, that's the same as delta K. Okay, so delta K, the uncertainty in K space, is proportional to the uncertainty in momentum space, but times a factor of h over 2 pi. And if you do the analysis, Heisenberg was able to show that these two uncertainties have to be greater than or equal to h over 4 pi or h bar over 2. Okay, you get the equal sign for one special case, and that is if I create a wave packet which is Gaussian in K, that'll also turn out, if you take the Fourier transform of Gaussian, that'll also be a Gaussian in X. So that gives you the minimum possible uncertainty. Every other type of wave packet will have a slightly greater uncertainty. Okay. Now, why don't these uncertainties show up in day-to-day life, okay, in the domain of classical physics? Okay. And ultimately, everything, as far as you know, is governed by quantum mechanics. It's just that in the classical world, when you're dealing with large objects, these uncertainties might be washed out. Okay? And you can understand that by putting some numbers, where assuming if I'm looking at the electron, which of course is a tiny subatomic particle in a Bohr orbit, say with a radius of 1 angstrom, you can then figure out the uncertainty in momentum, which would be this h over 4 pi times delta x, say assume that's 1% of the radius, okay? And if you see what the number is, and you compare that with m times v of electron, I'm not doing that math over here, okay? The mass of electron is 9.1 times 10 to the minus 34 kilograms, okay? You'll see that this uncertainty is a pretty large percentage of typical momenta of electrons, okay? On the other hand, if we had to do this calculation for me walking around, say, okay, with a certain velocity, you'd see that the uncertainty in my momentum when I'm walking around as a fraction of the momentum when I'm walking around would be tiny because my mass is so humongous, okay? So these uncertainties are important for subatomic particles, but these uncertainties on a fractional basis for large macroscopic objects are basically negligible, all right? So we are now on the cusp of writing down the mathematics of quantum mechanics. Are there any questions at this point? So it's very important that you have this physical picture in your mind about everything in nature having this wave particle duality. Okay, and that's a beautiful picture, right? So everything, photons, electrons, protons, neutrons, everything have this beautiful wave particle duality. All right. So that, like I said, led to the development of quantum mechanics, which is a strict mathematical formulation of these principles developed by Schrodinger and Heisenberg. What I'm doing is giving you the picture, mathematical picture of Schrodinger in terms of wave functions. All right. The wave function based Schrodinger picture leads to this famous equation, which is known as the Schrodinger equation in quantum mechanics, which is an equation in terms of operators. What is an operator? Well, we study operators in calculus all the time. So for example, if I have a time-dependent function, f of t, you can take the time derivative d dt of that, right? Which you can sometimes write as f prime of t, for example, right? So this is the time rate of change of some function of time. So d dt is an operator. Now, clearly, I'm not multiplying f of t by d dt, I'm operating on that, right? Similarly, suppose I am looking at the second derivative in position, d2 f, now something of x, dx squared. What it means is I take some function of x, I differentiate that once, that gives you df dx, and then I differentiate it a second time with respect to x, that gives you the second derivative, right? So once again, I'm not multiplying, obviously, I'm taking the spatial derivative once, and whatever the result is, I'm differentiating it again. Okay, so that's all there is to it, okay? So what Schrodinger said was, if I look at a particle with a certain mass, you can define the so-called Hamiltonian operator, which is the equivalent of the total energy of the particle. Now, what is the total energy of a particle in classical physics? Well, it's got two components. It's got the kinetic energy plus the potential energy, right? Kinetic energy is half mv squared, or equivalently, you can write that as p squared over 2m, where p is your linear momentum, mv, right? And potential energy depends on the problem in hand. If I'm looking at some one-dimensional problem, it'll be some function v of x, say, okay? So kinetic plus potential energy gives you the total energy, which corresponds to this so-called Hamiltonian operator, okay? And what the Schrodinger equation is, the Hamiltonian operator operating on what's called the wave function, which is this analog of this de Broglie wave, say, of electron, gives you the total energy times the wave function, all right? Now, word of caution, I'm giving you a simplified description of quantum mechanics. If you have taken a quantum mechanics course, and they'll explain basically the same equation in a slightly different language, but for our purpose, the simplified description is perfectly adequate, all right? The next thing that you have to do is figure out what form this wave function has and exactly what the quantum mechanical versions of these operators for kinetic energy and potential energy would be. Okay, so let's write them down and see what the consequences are. Okay, so first of all, what the heck is this wave function? Well, it's kind of this wave, de Broglie wave that we've already talked about, except that in quantum mechanics, this wave is going to be a complex number. Okay, so it has a real part, say psi real plus I times psi imaginary. Okay, so it's not a real quantity. It's got a real part and an imaginary part, where I, of course, is square root of -1, okay, the imaginary number. Sometimes we'll also call that J, but I'll try to be consistent. I'll call that I, but in the literature, sometimes it's also called J, okay? So that's your wave function, okay? So for example, an example of a complex wave function would be this one over here. Some amplitude A, e to the power, here I'm using J, I guess square root of -1, kx minus 2 pi nu, which is nothing but omega t, plus some phase term phi, okay? Now remember from your math classes that this is nothing but a cosine of this quantity plus I or j sine of this quantity, right? So this is a real part and an imaginary part by the Euler relationship, okay? Now, we've seen already that if I take the square of the amplitude of a wave, that gives you the intensity of the wave, okay? In the case of photons, that tells you the brightness of the electromagnetic radiation. So that tells you how likely photons are going to hit that location in space, right? So similarly over here, for matter waves, one finds that the square of the amplitude gives you the probability of finding a particle in space at that location. Okay, so psi amplitude square. So this is the amplitude, right? The magnitude of the amplitude square can also be written as psi star, which is a complex conjugate times psi. Okay, this is nothing but the same as psi amplitude square, is the likelihood of finding a particle between location x and x plus dx. Okay, so this is a function of, let me write this, a function of x so in general, psi is going to be a function of x, okay, magnitude square. Dx is the probability of finding the electron between location x and x plus dx. Okay, and this is also sometimes known as your probability density function. Okay, now if I have some probability density function, if I sketch it out in space as a function of x, now I'm plotting, say, psi magnitude square, and I get some function like this, say. Okay, so once again, between x and x plus dx, so this distance is dx, that tells you the probability of finding the particle between x and x plus dx. Okay, that's why it's called a probability density function. Now, question, what do you think I should get if I integrate this probability density function, psi magnitude square or psi star psi, from minus to plus infinity, going over the entire universe?
Should get 1.
One should get 1, exactly, because the particle's got to be somewhere, right? It's got to be in Austin or Dallas or Antarctica, somewhere in the universe, right? So this integrated from minus to plus infinity dx integrated should give you 1. Now, what if it doesn't give you 1? No problem at all. Suppose I got some value n. All that I need to do is divide the psi by square root of n, so that square root of n times square root of n in the denominator would cancel with this n, and I'd get 1. Okay, and that operation is called normalization of the wave function. It's just basically a scaling factor, okay? So that if the integral doesn't give you 1, you divide by whatever the area is under the integral, square root of that, and that makes sure that the integral will give you 1. And we'll be dealing with, obviously, normalized wave function. All right, so that's the first postulate of quantum mechanics. So everything is represented by a complex quantity, which in general is going to be a function of position, x, y, z, which I'm calling r, and time. So it will be a time-dependent function, because obviously particles can move in space and time and so on and so forth, all right? Where psi star psi, or psi magnitude square, is your probability density function, and that better be normalized. If it's not, you just do scaling to make sure that it integrates to 1. The second postulate is, for every classical quantity in classical mechanics or any experiment that you do in the lab, the corresponding quantum mechanical operators. So think of it as a quantum mechanical dictionary, all right? What are those operators? Well, in the case of position r, the corresponding operator happens to be the same, okay? If I'm looking at a one-dimensional problem, which is what we'll be doing, x will be x. Or if it's some function of x, say this potential function v of x, in quantum mechanics also it'll be this v of x, okay? Very straightforward. Now, what's a little bit trickier is the operators for momentum and energy. So it happens that for momentum, the operator is h bar, h over 2y over j, square root of -1. Sometimes we'll call it I also, times the grad function. Now, if it's a one-dimensional problem, I'll have some p of x. Now here, the operator will be h bar over j, or I, del x. Because the grad function, remember, it's del x times the unit vector along the x-axis, say, which I'm calling I. Don't confuse that I with the imaginary number I, plus I j del y k del z, okay? So I've used all these letters already. So these I, j, k with the hats are the unit vectors along x, y, z, okay? So don't confuse that with the imaginary number. That j is not the imaginary number. This is not the wave vector, okay? So these are the unit vectors with the hat on top of that, okay? In 1D, I have this, okay? And finally, for energy, it's minus h bar over j del del t, okay? Now, if you've taken a course in quantum mechanics, you may have seen this explained in a slightly different way. So I'm kind of taking a shortcut, but that's perfectly okay for us. Okay, so we'll just see if I use these quantum mechanical operators, how we can rewrite this equation, which is the Hamiltonian operator operating on the wave function. Hamiltonian operator being the sum of the kinetic plus potential energy gives you the total energy times the wave function. Okay, everybody with me so far? All right, and then the final postulate of quantum mechanics is, when you do an experiment in quantum mechanics, say on some macroscopic object, maybe a transistor or a diode, we know, of course, that it's made up of billions and trillions of electrons moving around in the crystal. You can think of each of those as being a quantum mechanical system. So then in classical mechanics, when I'm doing an experiment on a large number of, say, these electrons, what you'd be getting would be some statistical average of all these individual quantum mechanical experiments, if you will, okay? And what you measure in your lab would be a so-called average or expectation value, which is Q with this angular brackets. And the way you get that is you take this wave function, you operate on that with corresponding quantum mechanical operator, okay? Where these operators will be made up of these quantities or various combinations of those. Whatever result I get, you multiply that by the complex conjugate of psi and integrate over all space. This I'm looking at a three-dimensional problem. If it's just 1D, it will be dx, okay? And that's all that you need. But if it happens that the wave function wasn't properly normalized, to take account of that, you divide by this denominator over here. Because if this gives you n, okay, then you have to divide by the n, and that's what the normalization is. All right? Now, once again, mind you, I'm not multiplying psi by operator, I'm operating on it, multiplying that by the complex conjugate of the wave function, and integrating over all space. And then if divide by the denominator if it's not being properly normalized, okay? So keep this at the back of your mind, and let's see where that leads us. And I'll come back and, yeah.
In later material, are we going to be given forms of these equations, or are these things we should just memorize? And
you should just, now let me go through it, and then so you'll see that it's actually quite straightforward, okay? Ask me this question after I go through this slide, okay?
Okay.
So you'll be given this equation, but then the special cases you have to work out, okay? So let's see what the Schrodinger equation turns out to be in operator language. Okay, so once again, it's a Hamiltonian operating on the wave function, gives you the total energy times the wave function, right? But the Hamiltonian is given by kinetic plus the potential energy, where kinetic energy is p squared over 2m, and potential energy is some v of x, right? So you have to add these two terms. Now, what is the momentum operator? Well, we'll look at a one-dimensional problem, but in 3D, it would be this operating twice, right? Now, let's see if I have some wave function. Let's look at a one-dimensional problem. If I operate on that by momentum, say one-dimensional problem, what should I get? I should get h bar over j del del x, right? So that's my operator, right? But then to get p squared, I'm not just going to square this. Whatever the result is, I have to operate again h bar over j del x on whatever the result was, right? Now the h bar over j's, those can be multiplied. So h bar squared. What is j squared? -1, right?
-1.
And then if I'm looking at kinetic energy, which would be p squared over 2m. So for kinetic energy, you have to divide by 2m, okay? Now let's see what else is going to be there. Now, if I operate on on psi of x by del x, what will I get? I'll get del psi del x, right? But then I operated on it again. Does that mean I'm taking del psi del x squared? No. Whatever the result is, I'm going to differentiate again. Now, what do I get if I differentiate it twice? I get the second derivative, right? I'd get del square psi del x squared. So the quantum mechanical operator of kinetic energy which is p squared over 2m, works out to this. Everybody with me? That was the hard part. Okay, everything else is much straightforward. All right, so for kinetic energy, I'm looking at a one-dimensional problem now. It will be minus h bar squared over 2m, the second derivative of psi with respect to x. If it was 3D, you'd get three terms, del square x squared plus del square y squared plus z squared, and that will give you what's called del square, or the Laplacian. Okay, but we won't worry about that in this class. The second part is much easier. So potential energy would be some function of r, or in 1D, some function of x. So in quantum mechanics, it's the same. So it's some v of x operating on this wave function. But if it's just v of x, it's just basically multiplying it, giving you the total energy. What is the kinetic and what is the total energy operator? It's minus h bar over j del t. So end up getting this. And this is your famous Schrodinger equation, time-dependent Schrodinger equation. All right. Now, for the kinetic energy, it's always going to be the same expression, right? It's p squared over 2m. The only difference from one problem to another in quantum mechanics is the choice of your potential energy function, v of x. So what we'll do is next work out two special cases. You can think of these as worked out examples of this v of x. And what comes out of those solutions are some very interesting concepts, okay? So once again, the only difference from one quantum mechanics problem to the other is what form of v of x that you have. We'll work out two examples today, and on Wednesday, I'll point out, I won't solve it, point out the solution where the v of x could be the potential profile for the nucleus of an atom. Say a hydrogen atom, of course, now has a three-dimensional Coulombic potential. We'll see when the electrons have spherical orbits around those, what the form of the solution is, and so on and so forth. Okay? Okay, now the question, of course, then becomes, how the heck do I solve this? Okay, now this is a differential equation. Can anyone tell me if it's a partial or ordinary differential equation? I don't know how many of you have had a course in differential equations. Hopefully,
because you have two variables and one.
Yes, very good. So ordinary differential equation is if you have one independent variable, but here we have two, x and time. So it's a PDE. Now, in general, if you've taken a course in PDE, you'll have noticed that partial differential equations in general are harder to solve than ordinary differential equations, okay? So one standard trick that's used to solve PDEs is to convert them into a set of ordinary differential equations. And there's many tricks of doing that, but one very common trick is to use what's called the separation of variables. And that's what I show over here. It's a very simple technique. So what you postulate is this function of psi of x and t, you say that, hopefully it's not always true, but let's see if you can write that as a product of a function of x alone times a function of time alone, okay? So this function of psi of xt, I'll write as just a function of x alone, the psi of x, times a function of time alone, which I call phi of t, okay? Now, don't confuse this psi of x with this overall wave function. Notice that I'm showing it with a slightly different symbol of psi. So, that's what everybody does in the literature. So I wanted to be consistent with that. People use the same symbol for the spatially dependent part as for the total wave function, but with a different symbol for the wave function psi, okay? So this psi, notice, has a different shape as this psi. So the basic idea of separation of variables is this function of x and t, let's try writing it as a function of x alone multiplied by a function of time alone. That's the essence of the separation of variables. So I plug that into these differential equations, okay? Let's see what you get. Now, for the first term, I take the spatial derivative of this product of psi of x times phi of t, right? Now, notice this is a derivative with respect to x. So as far as this phi of t is concerned, because it doesn't depend on x, it's basically a constant that you can bring to the left-hand side of this operator, right? Similarly, on the right-hand side, this is a derivative with respect to time. So although I had del t of psi x times phi of t, I was able to bring the psi of x to the left of that, because as far as the time derivative is concerned, this is a constant, right? It's independent of time. That's a trick in the separation of variables. The next thing that I do is I divide everything on both sides by the product of psi of x times phi of t. Okay, the whole thing on both sides. And let's see what terms cancel out. Well, this phi of t, I was able to bring it out to the left of this. I'm not showing it that way, but then I divide by 1 over psi of x, phi of t. You'll find that this psi of t will cancel with this psi of t. Okay, over here, if I divide by psi of x, phi of t, both of these terms will cancel out, right? And on the right-hand side, if I divide by psi of x, phi of t, the psi of x cancels out, and I have phi of t in the denominator. Everybody with me so far? All right. Then once you do that, you notice that on the right-hand side, you have a new function of time alone, because you got minus h bar over j, you have phi of t in the denominator, del phi del t. So it's just a function of time alone.
I'm a little bit confused on
Okay.
why the phi of t canceled out on one side but didn't cancel out on the other side.
So I divide both sides by psi of x times phi of t. Okay. For the first term, the phi of t you can bring to the left-hand side of this operator, right? Because this is an operator with respect to x, right? So for the first term, the phi of t cancels with the phi of t. And what I'm left with is 1 over psi of x, and then this operator with respect to x. For the second term, if I divide by psi of x, phi of t, both of them can be canceled out. So I'm just left with v of x, okay? On the right-hand side, I had del t initially of psi of x, phi of t, but because the psi of x doesn't depend on time, I could have brought it to the left-hand side of that, right? And then I divide by psi of x, phi of t. So the psi of x is canceled out. So what I'm left with is 1 over phi of t, del phi del t. Is that okay?
Oh, so since you have the delta in front, you can't. Oh yeah, because it's delta phi t. Okay.
Right.
I forgot that it was different terms.
Sure. While on the left-hand side for the first term, you cannot cancel the psi of x term because you have, the second derivative with respect to x, right? Yeah, I wish I had a nice big blackboard to do it in steps, okay? All right, so on the right-hand side then, I end up with something which is just a function of time alone, equal to, on the left-hand side, you'll notice that all the phi t terms have canceled out. On the left-hand side, it's just a function of x alone. Okay. Now, what is the only possibility if I have a function of x alone on the left-hand side equal to a function of time alone on the right-hand side? They both must be equal to some constant, right? Because if you have some arbitrary function of x equal to some function of time, the only way that's possible is if both of them are equal to the same constant. So that's known as your separation variable, and we'll indicate that constant by the letter E, because I know the final answer. So that separation constant happens to be the total energy of the system, the sum of the kinetic plus potential energy. Okay, because since I know the answer, might as well choose the proper separation constant to begin with. Okay, now let's see what that gives us. The easier part is the time dependent part. Okay, so if both of these are equal to energy E, the separation constant, what do I end up getting? I get del phi del t. I bring this over to the left-hand side. So I'll get minus h bar over j. So j over h bar times E times phi of t. And then I bring it to the left-hand side, right? So this is this equation. Does everybody see that? So I've written both sides of the equation equal to the same constant E, which will turn out to be the total energy of the system. So that's why I'm calling the constant E. And if I do that, then the right-hand side gives you this. So that's the time-dependent part, all right? What is the solution of this? Well, this is a straightforward differential equation that you see again and again. The solution is an exponential. Phi of t is equal to e to the power minus j E over H bar T, okay? Now notice that is your Planck relationship. So E over H bar, I'm calling omega. So that's the angular frequency in radians per second by which this wave function is evolving, okay? So E over H bar equals omega, or E equals H bar omega. So that's the Planck relationship, looking ahead, all right? How about the left-hand side, the spatially dependent part? Here is the fun part, okay? So if you work out the left-hand side, okay, so once again, in terms of the separation variable E, and I know this slide is getting messy, but you can take my word for it, this is what you'll end up with. You'll get the first term, which is minus H bar squared over 2m, the second derivative with respect to position, plus V of x, psi of x. Because remember, I had the psi of x left over, right? So when I multiply throughout, I get a V of x times psi of x. This is not the total wave function. This is just a spatial dependent part of it, equal to E times psi of x. Okay. This is also known as a time independent Schrodinger equation. What we started out with was a time dependent Schrodinger equation because time was a variable. But here, notice time has been already taken care of with the first equation. So this is known as a time independent Schrodinger equation. This is also sometimes known as an eigenvalue equation for energy, because I don't know if you remember from your linear algebra classes, if I take a function and I operate on that function and I end up getting the same function times a constant, those are known as your eigenvalue equations, right? Now that's what I'm getting, right? Because I take some function psi of x, operate it on it with a very complicated function, which is the second derivative here and the V of x over here. I get back the same function times a constant. That's an example of an eigenvalue equation. So these energies are known as your eigenvalues or eigenenergies. And we'll see in a second, these correspond to the energies, for example, that you have in the Bohr orbits. And these functions are known as your eigenfunctions. The term eigen is a term in German, means proper function, okay? So operating on these eigenfunctions, this will be an allowed, the electron wave functions in your various Bohr orbits will give you the allowed atomic energies times the same eigenfunctions, all right?
I just want to make sure for
Yes.
the when you're taking the partial derivative, is that just completely independent from what you did with the 1 divided by phi of x, or if you, I'm having trouble memorizing all the variable names, but it seems like you got rid of the phi of x on the right side, and yet now it's back on the partial derivative equation on the bottom left.
Right, so I divided both sides by the product of psi of x times phi of t, okay?
Yeah.
And if see in each of these terms, I have 3 terms, right? 2 on the left-hand side and 1 on the right-hand side, right? And for each of these, some of these can be canceled out. So for the first term, the phi of t, because I could have brought that out to the left-hand side of the spatial derivative, that phi of t cancels with this phi of t, okay? But I'm
I get which ones cancel. I'm just confused because on the bottom left equation, you have a you have the of x term back, but that canceled when you did this division earlier.
Or that's because for the first term, I have the 1 over phi of x in the denominator, okay? For the second term, I only had the V of x. And on the right-hand side, I had the constant E, right? So this 1 over phi of x in the very first term, I multiplied that throughout, right? So if I do that, that disappears in the first term. I just left the derivative. For the V of x, I multiplied that by this phi of x over here, okay? And on the right-hand side, I end up getting E times phi of x. It's just algebra.
Okay, so you just multiplied a phi of x throughout the entire equation?
Right, because I had let 1 over phi of x in the first term, right? Because when I had divided by 1 over phi of x psi of t, for the first term, the phi of t was canceled out, but I still left with the 1 over phi of x. Sorry, my Greek, 1 over psi of x in the first term, right? For the V of x times psi of x, phi of t, initially I had canceled psi of x, phi of t, right? Because I divided throughout all the terms by psi of x, phi of t, all right? But then in the very last step, this 1 over psi of x, when I multiply throughout, that's where I end up with the v of x times psi of x once again, okay? Because remember, I initially 1 over psi of x, the first term, right? What I'm doing is I'm multiplying throughout by psi of x, so that disappears in the first term, but I get back the psi of x here and the psi of x over here, okay?
Okay.
I think the best thing might be, after the class, just try to do the separation of variables yourself, or you can look up any standard quantum mechanics book. And if you have questions, still, maybe ask me during office hours on Wednesday. Okay.
Okay.
Yeah. All right. So this is really the only term which will change from one quantum mechanical problem to the other. Like I said, this v of x will depend on what potential profile I'm imposing on my electrons. We'll be solving the electron problem. Okay. So you'll have different boundary conditions and different potential profiles, and depending on this, whatever v of x that I choose, I'll get different solutions of these eigen functions. The time-dependent part will always have the same solution. All right. And then you can write down the overall solution, psi of x and t, by taking the product of this time-dependent part with the spatially dependent part. Okay. Now, what you'll find when you do these solutions is, in general, you can write them as a sum of various terms like this with different eigenfunctions, psi of n. So when I solve this, I may get, say, psi of 1, psi of 2, different eigenfunctions. Okay, in general, let me call that psi of n of x times e to the power minus j corresponding eigenenergies, which I call En over h bar times t. So the t, it's e over h bar times t. Okay, so the t is not in the denominator, times some coefficients Cn. What this means is I can write down the total solution as a linear combination of different terms, different eigenfunctions, psi 1 e to the power minus j e1 over h bar t, with some coefficient C1, plus, say, C2 psi 2 e to the power minus j e2 over h bar times t, plus another constant C3 psi 3 e to the power minus j e3 over h bar times t, and so on and so forth. Okay, where I have to determine these various constants, C1, C2, C3, and some of them may be 0, depending on whatever the boundary conditions, initial conditions of the problem are. Okay. Now, once you get this, you can use a fancy language and say that for these wave functions psi and x of t, they reside in what's called a Hilbert space. Don't freak out. I'm just introducing the term so that, over on weekends you can impress your friends. Okay, I'm not going to expect you to, use these in exams or whatever. Okay, I just want to make the analogies. Okay, so these eigenfunctions, psi 1, psi 2, psi 3, etc., are the analog of your unit vectors I, j, k, say in three-dimensional space. Okay, so if I have a three-dimensional space, so x, y, z. Okay, tell you what, let me backtrack. Instead of calling these unit vectors I, j, k and confusing you, let me call it x, y, z unit vectors. I think that'll be less confusing. Okay, so x, y, z are your unit vectors along the x, y, z axis, say. Okay, and then if I consider any vector v, I don't want to confuse that with this potential profile. Let me call it some other vector, say maybe let me call it a vector b, say. Okay, so vector b can be written as unit vector x times a component along the x-axis plus y component along y plus z component of the vector along the z-axis, right? in three-dimensional space. So these eigenfunctions that I was just talking about, psi1, psi2, psi3, etc., are your analogs of your unit vectors x, y, z in three-dimensional space. The only complication is, unlike three-dimensional space where you only have 3 unit vectors, for these eigenfunctions which reside in this fancy Hilbert space, it's not three-dimensional space, you can have an infinite number of these unit vectors. So it's an infinite dimensional space. Okay. I don't know if you saw any of these in your linear algebra classes. Okay. Don't worry too much if haven't, because like I said, all that I wanted to do is to give you some physical intuition of what these eigenfunctions are referring to. Okay, so think of them as being the analog of these unit vectors, and just as you can decompose a vector in terms of these unit vectors times its components, similarly over here, any function ultimately can be written in terms of linear combinations, C1, C2, C3, where the C1, C2, 3 correspond to your, say, BY, BX, BY, BZ, times the unit vectors, psi1 e to the power minus j e1 over h bar t. So that would be like your unit vector x, psi2 e to the power minus j e2 over h bar. So that'll be like your unit vector y, and so on and so forth. Does everyone get the correspondence? I know the first time you see this, the math may be a little bit problematic, but if you've taken 325, the math in quantum mechanics is actually a lot easier than in Maxwell's equations, right? Because in Maxwell's equations, you get, vector quantities E and H and 4 different differential equations. Where in quantum, really, it's just a scalar quantity. It's complex quantity psi, but it's not a vector quantity. And you just have one partial differential equation, which breaks out to one universal time-dependent equation, and then the space-dependent part, which depends on the problem, v of x. Okay, so the math is actually a lot easier than in EMAG, for example. Okay. Now, once I see that I can write down any wave function as linear combinations, sum over n, Cn times these various eigenfunctions, you can kind of explain this final equation over here. Okay, so basically, when I calculate the expectation value, what I'm doing is I'm operating on these wave functions, which can be written as linear combinations of eigenfunctions by some operator. So you'll get various eigenvalues of that operator along this eigenfunction. So these are your components, say bx, by, bz, and then multiply by the complex conjugate. So basically what this is, it's sort of the weighted sum of the eigenvalues, which would then give you the overall average quantity. Okay, let me work out 2 examples, and hopefully that'll make the concepts clearer. Okay. So what I'm going to do next is basically work out 2 problems for 2 different values of v of x and see what you get. Okay. So the first problem is the simplest of all in quantum mechanics. We'll assume that this v of x, this potential energy v of x, is a constant. You can't get anything simpler than that. Okay. And not only that, because potential energy is a relative quantity, we'll choose the reference of that potential to make the constant equal to 0. Okay, so we choose v of x to be a constant, and then we choose a reference so that the constant happens to be 0. Okay. Now, physically, what does that correspond to? Well, that corresponds to a free particle, because in classical mechanics, if you have a constant potential profile, so v of x, okay, we know that the force is related to the gradient of the potential minus dv dx, right? So if v of x is a constant, the force on that particle is equal to 0. And that's what's called a free particle. And we'll see that the solution of that in quantum mechanics is a plane wave. Why is that? Well, if I set v of x equal to 0, the differential equation becomes very straightforward. It becomes, the first term is minus h bar squared over 2m d2 psi dx squared, the second term is 0, equal to E psi, right? I multiply by 2m over h bar squared, and I bring everything to the left-hand side. So what I'll end up getting then is plus 2me over h bar squared psi equals 0. See what I've done? So I multiplied by 2m over h bar squared, and I bring everything to the same side. So that gives you d2 psi dx squared 2me over h bar squared equal to this. Okay. This quantity 2me over h bar squared, I call it a new variable k squared. So then I get d2 psi dx squared plus k squared psi equal to 0. What is the solution of that? Well, that's a famous second order differential equation that you see in many classes, hopefully. Okay. You may recall that can be written as a product, sum of some A sine kx plus B cosine kx, or using the Euler relationship. Remember, in Euler expressions, you have e to the power I kx can be written as some A prime sine kx plus say some B prime cosine kx. Okay, so the point is the solution of a second order differential equation could be written either in terms of sines or cosines, or equivalently in terms of e to the power I kx or e to the power minus I kx. Okay, in this case, we'll choose this exponential form of the solution. Okay, so the solution of psi of x will be some amplitude a times e to the power, not be consistent, j and I are the same. Okay, it's both equal to square root of -1 kx. But then remember the time dependent part, right? So for the time dependent part, the solution was the same in every case. It's given by e to the power minus j e over h bar t or omega t. So to get the overall wave function, I have to take the space part, multiply by the time dependent part. So if I do that, I end up getting this. So that is the solution of a plane wave corresponding to a free particle. That's the simplest possible solution you have in quantum mechanics, where I've chosen v of x equal to a constant, and I can choose that constant equal to 0 by choosing a suitable reference potential energy. Everybody with me? So you can think of this as a worked out example, a very important one.
I'm a bit confused on the conversion you did for the E equals P squared over 2M to that longer equation. Like, is that what you were multiplying from? I'm a bit confused on what that first equation you were working on is from on this page, not on that page.
Next one. This one?
Yeah, the one under like operators correspond to physical
Oh,
quantities.
yes, this one?
Yeah, I'm not sure where you pulled that from.
Oh, so that's this time independent form of the Schrodinger equation over here, this one over here, right? So this is minus h bar squared over 2m, second derivative with respect to position, plus v of x, but now I've chosen v of x equal to 0. V of x was chosen to be a constant, okay?
Okay, so you set that to 0, so there's only one term on either side. And then you divided it, or you multiplied it by 2m over h
bar squared.
Okay.
Yeah, h bar squared, okay? So that gives you on the right-hand side, that will give you 2me over h bar squared, but there's a minus sign, so if you bring everything to the same side, that's what you end up getting, right?
Okay.
And I'm now writing the 2me over h bar squared equal to a new variable k squared, okay? And I'm choosing these variables because I know the final answer. So I'm choosing something so that, we don't have to change symbols later on, okay? So this k will work out to be the wave vector 2 pi over lambda, the de Broglie wavelength, okay? Since I know the answer, I might as well choose variables which will make sense later on, okay?
The 2me over k squared is equal to k squared here?
Yes. I'm introducing, for right now, k squared is just a new constant that I'm using to represent 2me over h squared, okay?
Just setting it equal to a new variable.
Right. later on will turn out that new variable will be the wave vector k that we have already introduced. All right. Okay, so by solving this differential equation, the standard solutions can be written in terms of sines plus cosine terms, or equivalently in terms of e to the power I kx plus another term would be e to the power minus I kx. So in this case, I choose this exponential forms. So e to the power, let me be consistent, let me call it jkx, okay, because I'm calling it j, okay. So e to the power jkx times e to the power minus j omega t, where the j omega t comes from the space time dependent part of the Schrodinger equation. And that solution, like I said, is always going to be the same. It's only the space dependent part which changes from problem to problem as I change the v of x terms, okay? And what I'm doing is, think of this as a worked out example where the v of x was a constant, where I set the constant equal to 0, all right? So that's one term. Now I'd get another term with another amplitude, say b e to the power minus j kx minus j omega t. I'm not showing that over here, okay? But in general, you'd have two terms. Now this term, as shown over here, corresponds to a plane wave propagating along the positive x direction, while the second term that I'm not writing, e to the power minus j kx, would correspond to a plane wave propagating in the negative x direction. Now, in some cases, if I have, say, reflecting boundaries, those two plane waves can then give you standing wave patterns, which I could write in terms of sine and cosine functions. The next problem that I work out will illustrate that. But before I go to the next problem, let's see if I can make use of this final formula in quantum mechanics to glean some information. And what this was I said that the expectation value, or the average value that you can expect in a quantum mechanical calculation, is given by this expression, right? You operate on the wave function by an operator, multiply the result by the complex conjugate, integrate, and then if the wave function wasn't normalized, you divide by this denominator over here. Let's use that and try to come up with expected values of momentum and energy using the corresponding quantum mechanical operators, okay? Now for momentum, it's given by h bar over j grad function if it's a three-dimensional problem, or del x if it's a one-dimensional problem. Let's see what that gives us, okay? So assuming it's a 1D problem, p of x would be this wave function that I've determined. Here I'm just showing the space-dependent part because the time-dependent parts ultimately cancel out, so I don't want to clutter up the picture. Operated on by the wave function, operated on by the momentum operator, which is h bar over j del x. Whatever result I get, I multiply by the complex conjugate of this wave function. What is the complex conjugate of that? It'll be whatever a, could be a complex number, a star, complex conjugate of e to the power j kx gives you minus j kx. Okay, now let's see what I get. Now, what do I get if I take the derivative of an exponential? Does anyone remember?
Of like e to the something?
I just get this exponent, right?
Yeah.
Where the j will cancel out, I'll be left with kx. Sorry, no, k, and not I won't have the x, of course, right? So I'll get j kx, right? So then the j's cancel out, and I'll be left with h bar kx, and I get back this original exponential function again. That I multiply by this complex conjugate. So the a star a will give you a magnitude square. E to the power minus j kx will cancel with the e to the power plus j kx. And in the numerator, what I'll be left with is h bar kx. Okay. Now this wave function is not normalized to begin with because I have some unknown amplitude a. So the denominator I have to multiply by psi star psi. If I do that, a star a will give you a magnitude square, and then psi star psi, the exponents cancel out. So I'll get a square in the denominator. Now I'll notice in this particular case, and it's really only in this particular case, you have a bit of a problem. And the problem is a magnitude square is a constant times d integrated with respect to x will give you what? If I integrate from minus to plus infinity?
Shouldn't it just give you 0?
No, if I integrate, if I integrate a constant over minus to minus plus infinity, will give you infinity. Okay. Similarly, in the numerator, it turns out you'll also get in the numerator also, for plane waves, you end up getting infinity. And that's, of course, a problem because you get infinity divided by infinity. So what do you do? So what you do is, instead of integrating from minus to plus infinity, you say that, okay, I'll integrate first from minus L to L. So I construct an artificial box, okay? Minus L to L, same in the numerator, minus L to L, okay? And you'll find that you'll end up getting a squared times L. Similarly, in the numerator, you'll get L, and the L's will cancel out, okay? And once the L's have canceled out, then I take the limit of L going to plus or minus infinity, okay? So by that time, the L's have already canceled out. So then, you can pretend that the limits have gone to infinity. And that's how you do this particular problem, okay? This is the only case where you have to play that trick when you have plane waves, because you end up getting these infinities in the numerator and the denominator. For other wave functions, you don't have that problem. So this is a trick that you get to use in one of the problems that I've assigned. All right, so what I end up getting is, for this expectation value of the momentum along the x direction, is h bar kx, okay? And that, of course, is nothing but the de Broglie relationship. You can also write that as h over lambda wavelength in the x direction. You can do the same thing for the expectation value of the energy. So now I have to look up the operator for energy, which is minus h bar over j del del t, time derivative. And because this is a time derivative, for the wave function, I better keep the time dependent part, okay? I can actually now ignore the space dependent part because that'll cancel out, okay? Go through the same math. I'd ask you to do that on your own. So if you take the time derivative from here, you'll get j omega, okay? Once again, you have this problem of both the numerator and the denominator giving infinity. So initially you integrate from minus to plus L, minus to plus L. The L's will cancel out, and then you pretend that the L goes to plus or minus infinity. But anyway, if you do all of this, you'll end up getting the expectation value of energy works out to h bar omega, which is nothing but your Planck relationship. Okay, h bar omega or h nu. And once again, this relationship between momentum and wavelength, and this relationship between energy and frequency are going to be true for everything, for electrons, photons, neutrons, whatever. But in some cases, you may also be interested in relationships between quantities in equation 1 and 2, such as between energy and momentum, okay? Now, those will depend on the type of particle that I'm dealing with. Now, since our case in this class will be dealing primarily with electrons, let's see what that relationship would be. So for electrons in free space, the energy is given by just momentum squared over 2m. That's a kinetic energy term. The potential energy has been set equal to 0 because I've chosen a reference so that the constant potential energy is equal to 0. I've already calculated the momentum as h bar kx. So by plugging that in, p squared gives you h bar squared k squared over 2n. Okay? This relationship, if I plot it out, if I plot energy as a function of k, I'm dropping the subscript x over here, okay? What is the form? It's a parabola. This is sometimes called a dispersion relationship or band structure. Okay, so you'll see when electrons move in silicon or germanium or other semiconductors, they'll have this parabolic dependency between the energy of the electron and the wave vector, but the wave vector is basically proportional to the momentum of the particle or the velocity of the electron. So I want you to, pay special attention to that, because a lot of the problems in semiconductor physics will have some sort of a parabolic relationship. In a semiconductor, you don't be an exact parabola, it'll be a distorted parabola, but this is a good starting point, okay? Now you can also plot the energy as equi-energy contours as a function of kx, ky, kz, and then in this particular case, you get these spherical surfaces, okay? So these are constant energy contours, now plotted as a function of kx, ky, kz for the 3 components of momentum, okay? So if I write down E equal to h bar square over 2m kx square plus ky square plus kz square, that's a formula of a sphere. So for different constant values of energy, you get the so-called equi-energy surfaces. Okay, so here I'm plotting energy as a function of k. Here I'm plotting constant energy surfaces as a function of k, x, ky, kz. Okay. Now we won't be dealing with this sort of a picture that often, but I just wanted to throw it out. And I'd hoped to get to the next problem, but I guess we'll start off with this on Wednesday. So the next problem that we'll solve is a different choice of v of x, where we'll assume that v of x is a constant, but now not over all space. It's only going to be constant between, say, 0 and L. But then at 0, the v of x goes to infinity. At L, it goes to infinity. And I want to solve this Schrodinger equation, the time-independent part of the Schrodinger equation, under those conditions. So now I can't set v of x equal to 0 everywhere. I can choose a reference to make it 0, but only in a finite region between 0 and L. And then it'll go to infinity at x equal to 0 and x equal to L. Okay. Now, if my potential energy goes to infinity in these pink regions, for electron to appear in those pink regions, what will be the energy of that electron? If my potential energy is infinity, that plus the kinetic energy would give you
Infinity.
Infinity. Now, can have anything have infinite energy in nature?
No.
And that answer is no. So how do you think I could explain that in the language of quantum mechanics? What would be the probability of finding the particle in those pink regions?
0 chance.
0 chance. So what must the wave function be? Wave function magnitude
Between
squared is the
0 and
probability.
0.
And yeah. So now on Wednesday, we'll start with this. We'll basically solve the Schrodinger equation with a constant potential, but now we have to apply boundary conditions that psi of 0 and psi of L must be equal to 0, because particles can't have infinite energy. Okay. So what we'll do is on Wednesday, we'll start with the general solution that we already did for the free particle, but now it's not free particle everywhere. It's only free between 0 and L. Then we'll choose this form, a sine kx plus b cosine kx, okay? And I'll put boundary conditions, x equal to 0 and x equal to L, wave functions must vanish, okay? And by doing so, you'll get this sort of a wave function, and then using that, we'll solve for the energy and the momentum and all that, okay? So this is sort of the second worked out problem. I'll go through this in great detail on Wednesday, because it's going to be very, very important for us. All right?
Thank you.
Anything else? Okay, thank you.
Thank you, Dr. Banerjee.